Hello, this is Steve Mackay from the Engineering Institute of Technology, doing a presentation of routers and switches. Hopefully all you can hear me. This is basically a quick rundown on routers and switches in, dare I say, 10 minutes, maybe a bit longer, and obviously focusing on TCP/IP protocols. So we do this every week. We do a presentation or a live session. Why do we do it? Yeah, good question. Basically just to give a bit of PR on what we do as training and education. We're an engineering education provider, and we focus on engineering sort of topics ranging from instrumentation through to process control through to obviously IT and communication topics. So briefly discussion about TCP/IP, how routers and switch work, look briefly at routing basics and a few troubleshooting tips. Obviously, there's quite a lot of material here to cover, so I'm going to try and do it in a reasonably efficient time. Obviously, the question is why bother? Well, as I was saying to one of our IT guys today, unfortunately, or fortunately, whether you like it or not, IT and communications is a key part of every engineering function today. I would dare say, even if you're an electrician or a mechanical guy, you need to have some idea of what's going on with TCP/IP. It basically makes the world tick. Now, this little diagram OSI model is obviously a little bit comprehensive, what we're trying to do. But if you look at this diagram, you'll see basically at the bottom, data link and the physical layer is where we deal with Ethernet. The IP protocol focuses with the network layer. You can see over here. And the transport layer is, of course, the UDP protocol, which we're not going to worry about too much today, but the TCP is the transmission control protocol. And then at the application layer, we've got various things which you come across, HTTP, which is your web site, email, and this is basically referred to as a process and application layer. So there's actually a 7-layer model, which is open system interconnection model, which is simplified by the TCP/IP protocol into 4 layers, 1, 2, 3, 4. The IP protocol is the key here, and that's a 32-bit address, but as I was pointing out to everyone today, the version 6 uses 128-bit. So really, IP is broken up into a net ID and a host ID. Host refers to your computer, and the network, it has a unique number referring to the network you're on. MAC address is a 48-bit address, Ethernet, media access control, and every card, Ethernet card, has a unique address, hopefully, unless you've manufactured your card in some godforsaken part where they don't adhere to the convention, but that's unlikely. IP address is 32 bits. And as I said, it's broken up into a host and a net ID, and you often see it referred to as dotted decimal notation. 2 parts. Transmission control protocol is the next level above the IP protocol. This is called connection oriented. In other words, you send packets out, you get a confirmation for every packet you send out, and as a result, it's reliable. You have to establish the session, and then eventually when you finish the session, you break it down. Unfortunately, a lot of overhead, so if you're sending video, you're not going to use TCP because it's a bit too slow. So it has various functions. It's not going to worry about here. The other sort of, should we say, addressing, which is not really address, is a port, and that's, for example, Modbus protocol has a particular port. So there's 3, if you can call them addresses. The MAC address, IP address, which is 192.168.0.1, and then a port number, which is relating to the protocol used. So you have a source port and a destination port. The other protocol is the UDP protocol, which is same level as the TCP, and this is used for sending stuff like video frames. Application layer protocols, as I said, are right at the top. Now, just to look at how a router and switch operates, obviously routers are used to connect multiple networks. and they work at the IP protocol level. So routing is active moving information across the network, between networks. Different ways of measuring a routing are the path length, reliability, delay, bandwidth, load, communication costs. These are all part of the decision of how to route or route your packets. Components of a router, well, basically it's a computer. So it's got CPU, BIOS, operating system. Cisco is probably the most famous. Motherboard, and then I/O ports to connect to the different networks, different internetworks. Two methods of operation: static routing and dynamic routing. Static routing, you often hear where everything's fixed, and dynamic routing is different ways of doing it. So distance vector, link state, and hybrid approaches, combination of those two. Static routing, you basically configure exactly where the packets are going in. The network administrator does it, and perhaps it's quite good from a security point of view, which, as we all know, the hackers are waiting to get into your network as soon as you put a router on to connect to a internet. Two methods of dynamic routing: distance vector, link state, and hybrid, which is a combination of those two. Distance vector, probably the most famous one is RIP, Routing Information Protocol, and that basically has a table of its connections, what each router is connected to, and that passes through to the network, to the other routers who are next door to it, and will then update their tables. Advantages are very simple and uses only number of hops to get from one point to the other. Drawbacks: takes a bit of time to converge to new understanding of the network if you've got 20 or 3 different routers all connected together. And of course, bandwidth and traffic levels you don't take into account here, and you probably would need to take into account for a sophisticated network. So they don't work always that well. Link state is probably the next version, next level up. Shortest path first protocols. And this is where things get a little bit more difficult. I'm not going to worry too much about this. The advantage of the link state is that they're pretty good with handling changes in your topology, in other words, the structure of a network. They're lower overheads, and they're better to scale if you increase the size of your network. Hybridized routing, which is a combination, uses distance vector like the RIP protocol, and they converge more rapidly, but add some of the overhead link state, and probably the most famous example is the IGRP. Convergence is the concept that you use when you make a change to the network, the structure, lots of routers all connect together. How quickly do the routers work out what the new structure is? That's convergence. So routing protocols, as I said before, RIP, distance, and then IGRP and OSPF, probably the most famous ones. Routing Information Protocol, RIP, where you pass copies to your media tables. Limitations are hop count is every time you go through a router, that's a hop. It's fairly inflexible, but for simple networks, pretty effective. So this is the RIP package. Not going to worry too much about this routing table. Routing database basically contains your IP address, the gateway, distance, route change flag, and then timers. RIP algorithm. RIP2 is a slightly more sophisticated version of RIP, in brackets 1. Allows you to have authentication, subject direct mask, next hop IP addresses, and multicasting. There's a RIP2 packet. Not too worried about that. The next protocol, which is a more sophisticated than purely distance, is the Interior Gateway Routing Protocol, IGRP. And the goals are for stable routing, and you get a pretty quick response to changes with very low overhead. And obviously far better than just distance. The metrics here which you use to measure your routing are hop count, packet size, links bandwidth, which, as you would have seen, is missing from the RIP protocols. Delay, loading, and reliability. These are all metrics that you used. So you get a formula here to work out the optimum routing reliability added in. Basically, you may have unreliable links. IGRP, some of these disadvantages are it doesn't include subject work mask information. The next one up, which is a bit more sophisticated, is OSPF, Open Shortest Path First. Just want to mention that. And just let's have a look at simple troubleshooting tips. Basically, first thing is to have a good knowledge of networking protocols, understand the topology, and some troubleshooting tools to fix problems. Hopefully, you can do it without luck. So as far as the network troubleshooting is concerned, you need to look at utilization of the Ethernet network. If you have low utilization but high errors, you could have a problem with one of your Ethernet cards. TCP/IP utility programs for troubleshooting. Probably the most famous one is ping. Ping the IP address, see it's there. Traceroute gives you a record of where the packets are going. Traceroute or trace it on some implementations of the operating system, ARP and RIP query and netstat. These all give good examples of they give you a quick utility view of your network. Just different combinations here. One of the interesting things here, actually network congestion, which is quite interesting, is if you ping a remote computer, you may say it's got a 700-800 millisecond delay. That's around trip time. You may wonder where the delay is. Excuse me. Trace it will actually help you, or Traceroute will help you find out between which routers do you have congestion, and then you may need to look at what's going on there and reroute your packets. Okay, that's about it from me, Steve Mackay. Just a quick view of routers and switches, and that's about it from Steve Mackay, Engineering Institute of Technology. Thank you very much for listening this far.